This is our should be last video in 7.2, talking about normal distributions and some word problems with there. And we'll also get to 7.3, which is really quick as well at the end. Okay, so another example, IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. Remember, IQ is one way of measuring intelligence. There are certainly some debates on whether it's the best, most appropriate way to measure it or not, but we'll assume it's okay for the sake of this problem. Okay, the mean, it says the mean is 100 and the standard deviation is 15. So we could count by 15s, 115, 130, 145. Now notice as we go this way, our IQ scores are going up. That means the people are getting more and more and more intelligent as we go, or their IQ is higher at any rate. If we go to the left, we count by 15s, 85, 70, 55. Usually 3 standard deviations is about as far as we would go or count. Okay, they say people are considered intellectually very superior. That means extremely smart. If their score is above 130, what percentage of people fall in that category? Okay, well 130, now notice 130 is at the second standard deviation mark. Okay, so these people are pretty smart. They're 2 standard deviations above the mean. Okay. People are very intellectually very superior if their score is above 130. So that's higher than 130. What percentage? Remember, pick your favorite P word, probability, percent, proportion. So we are looking for what percentage of people are above 130. We know the cutoff score. We're looking for the area. Okay, so that means we're going to normal CDF this one. When we pick normal CDF, it wants the lower bound, which is 130, then the upper bound, which would be infinity, but we don't have an infinity button, so 1E99. Then our mean, the mean is 100, and the standard deviation, which is 15. I ran out of room there, sorry, had to loop over. All right, so I'm going to type that in my calculator. Second vars, normal CDF, lower number's 130, 1E99 is the upper, mean of 100, standard deviation of 15. Remember, if you have an 83, it will not prompt you for those items. You have to just type them in yourself. And we get 0.02275. Okay. Now, remember, we know the cutoffs. We're looking for area. Normally, we would round area to 4 decimals, so 0.0228. Okay. But keep in mind, they wanted the percentage. So even though this is the decimal, we're going to give our answer as a percent. So as a percent, remember, move the decimal twice, it would be 2.28%. Okay? So 2.28% of people fall into the intellectually very superior category. Can't spell today. Intellectually very superior category. Okay. Part B, if we redefine the category of intellectually very superior to be scores in the top 1%. So in other words, if we're no longer sticking with the cutoff score of 130, but instead we say, you know what, we only want 1% of the people to be up here. Because right now there's 2.28% of the people that are intellectually very superior. And that's just too many. We think it should be only 1%. So what should our cutoff be if we only want 1% to be intellectually very superior? So remember, we got to give this as an area. So it's 1%, but as a decimal, that would be 0.01. Well, if 0.01 is the area up here, 1%, then that leaves 99%, or 0.99, down here. Don't feel bad. That's all of us, pretty much. Okay? So this time, we're not going to normal CDF it. We're going to inverse norm it, because we know the area, it's the cutoff we're looking for. So remember our calculator, assuming you're using an 83 or one of the older 84s, wants the area to the left, to the left, to the left. So 0.99, the mean is 100, standard deviation is 15. we get 134.895. Now remember, this is a cutoff number that we're finding, so we probably want to round that off to probably a whole number, actually. I don't know that you can get a decimal score in an IQ test. So to the nearest whole number, this would be 135. So 135 is the cutoff for the top 1%. So if you got a 135 or higher, you would say, yeah, I'm in the top 1% of the smartest people. Okay? All right. This is an interesting problem. I think this one's kind of funny. The lengths of human pregnancies are approximately normally distributed. That means it is okay for us to draw a normal distribution. With a mean of 266 days. That means, the average human pregnancy is about 266 days. Standard deviation is 16, so we could count by 16s. 266 plus 16 would be 282. Another 16 would be 298. Another 16 would put us at 314. Okay, we could count down by 16s. That would put us at 250, and so on. Okay, now keep in mind that the further you are to the right, the longer the pregnancy lasts. The further you are to the left, the shorter the pregnancy lasts. Okay, which can be concerning if it's too short, because that's when you have premature babies that might have some health problems or something like that. Okay, in a letter to Dear Abby, a wife claimed to have given birth 308 days after a brief visit from her husband who was serving in the Navy. Given this information, find the probability of a pregnancy lasting more than 307 days. What does the result suggest? Okay, so now think about this here. She gave birth 308 days after her husband came home from the Navy. So he came home from the Navy, and then apparently he went back because he was just there for a brief visit. So 308 days is like right in here. So she had a really long pregnancy. Or perhaps her husband is not the father of the baby. Okay, that's what they're getting at. They don't say that in words, but that's what they're getting at. Okay, so 308 would be around here. Find the probability of a pregnancy lasting more than 307. So they are asking for the probability that X is greater than 307. So if we put this cutoff here at 307, what is the probability that we're out here? I like to put my cutoffs below. Okay, well, we know the cutoff. It's the area that we're looking for to represent the probability. So we are going to choose normal CDF. Our lower bound is 307. Our upper bound is infinity, but we don't have an infinity button, so 1E99. The mean was 266. Standard deviation is 16. All right. Oops. Oh, sorry. I hit inverse norm instead of normal CDF. That was a problem, wasn't it? Let's try that again. Normal CDF, not inverse norm. I wrote the right thing, but I hit the wrong button. Okay, so normal CDF, our lower bound is 307. Our upper bound is 1E99. 266 for the mean, 16 for the standard deviation. And we get 0.005196, blah, blah, blah. Now remember, we knew the cutoffs. It was the area we're looking for, and we round area to 4 decimals, so 0.0052. Now think about what that means. That means that the probability of a woman's pregnancy lasting more than 307 days, because she gave birth on day 308. So the probability of pregnancy lasting more than 307 days is 0.0052. Or as a percent, that would be, move the decimal twice, 0.52%. That's less than 1%. Okay? So what does that tell us? That tells us that although it is possible for a pregnancy to last 308 days, it is a very small probability of that happening. So I would say in this case there is some questionable paternity. It's possible that her husband was home for that one-day visit, and it's possible that it's his baby, but it's not super likely. It's not a very high probability that the pregnancy would last that long. So we're not saying he's not the father, but we're not saying that either. Okay? All right, another example here. If we stipulate that a baby is premature, if the length of the pregnancy is in the lowest 4%. Okay, so premature babies are down on the left end. And we say they're premature if they're the lowest 4%. So they are giving us an area. They're telling us that this area is 0.04 for 4%. Find the length in days that separates premature babies from those who are not premature. So we are looking for this cutoff. We want to know how many days does the pregnancy last before we start saying, oh, that baby's premature and this baby is not premature because the pregnancy was longer than that. Since we know the area and we're looking for a cutoff, we are going to inverse norm this problem. Inverse norm, we always give the area to the left, which is 0.04, and then our mean and our standard deviation. Picking inverse norm, the area to the left is 0.04, mean 266, standard deviation 16, 237.989 days. I think in this case it makes sense to round to the nearest whole number. I'm getting a little bit too specific to start breaking it down to partial days. So I would say that premature babies came from a pregnancy of 238 days or less. Okay? Or if they were over 238 days, it was not a premature baby. Okay? All right. Last little part for this here. So far, all of the examples that we've looked at, the premature babies, the reading speed of 6th graders, the IQ scores, the women's heights, all those different examples, we have had really large data sets. Those are all things that are readily available to us. Okay? Probably the first thing you do at any doctor's appointment is get on a scale and get on. They measure your height as well. So we have lots and lots of data on that. Pregnancy, we have lots and lots of data on how long pregnancies last. Okay, so if you have lots of data, you know it's from a normal distribution. But sometimes we only have small data sets. Maybe, it's a new illness that has just been discovered, very rare. Not very many patients have ever had this illness. So we're not sure whether the data is normally distributed, okay? Maybe it's, U.S. presidents, and we're looking at, what's the average height of a U.S. president. There's only been like 40 of them. So that's not a huge data set. We don't know if there's necessarily a normal distribution there or not. So for this reason, we need to establish, if you have a small data set, whether or not you're dealing with a normal population or not. Because if it's normal, we can use our normal CDF, we can use our inverse norm, we can work problems. But we need to know if it's normal or not. Okay, so what they do is they take all the data and they say, okay, we're going to graph all the data on the x-axis, and we're going to find its z-score, and we're going to put all those z-score conversions on the y-axis, and we're going to put a dot. So maybe, President Obama was this height and his z-score was this number, so that dot's for him. And President Trump, his height and his z-score puts a dot right there for him. I'm just making up where those dots will go. Okay, so what happens is, if the data really is normally distributed, those data points there will be in a pretty straight line. However, if the data set is not normal, there will be one or more of those data points that is not very close to this line. It might be out here, off the line by quite a bit. Okay? So when that happens, we say, hey, this is not a normal distribution. The name of this graph, by the way, is called a normal probability plot. Some people call it a QQ plot, but our book calls it a normal probability plot, and that's this graph that I'm looking at right here. Okay, so if this was our data, our original data, the z-scores, and we saw a dot that was not very close to the line here that the other dots were in, we would say this is not normal. No, not a normal distribution. That means it would not be acceptable for us to work problems using normal, CDF, and inverse norm. It's not a normal distribution. Okay? This is not linear enough. Now what you may notice, it's kind of faint, but you may notice these little curves below and above the line. Those are kind of the scope of how much wiggle room we're allowing it to be. So any dots that are kind of outside these little curved lines, we say, yeah, they're too far out, and that's why they're not linear. Okay, so graph number 2. Notice all of these data points were pretty close to the line. And they were inside those little curved lines. This one's getting close, but it is inside. So I would say, yes, this data set is normal, and it would be appropriate for you to work problems using normal, CDF, or inverse norm. Third example here, looks like there may be a few dots that are not within the little window that we're giving it. So not normal. It's not linear. And in the last example, they don't give us the little curves, but I think all of these dots are real close to that line. So I'm going to say, yeah, that's linear. So this is a normal distribution. Okay?